Matematika. Today we're going to do 1.12b, a transformation of functions. A transformation of a function is a change in the position or shape of its graph. So position and shape of its graph. There are several types of transformation. So we're going to start with reflection. A reflection is a transformation that produces the mirror image of a figure across a line. And the line we are talking about is the x-axis and the y-axis. So a reflection across the x-axis can be represented algebraically by g of x equals negative f of x. So when you can see a negative in front of the function of x, that means it reflects across the x-axis. A reflection across the y-axis can be represented algebraically by g of x equals f times the negative x. So when the negative is inside the parentheses, that means it is reflected across the y-axis. And that's one thing you have to remember. When you see the functions are written in that manner, so you know where the reflection happens, whether it's across the x or across the y. Let's look at the sample figure in the graph. Reflection across the x. This is our x-axis right here. So the g of x is negative f of x. So if this is our graph, right, it reflects across the x. So if we have a space here, if this is 1, 2, 3, 4, when it will reflect also 4 spaces across the x-axis. Same thing with the other points here. On the other side, when it's reflect across the y, okay, the negative is inside the parentheses. So how many places or how many space do we have? 1, 2. Across the y, it's also 2 spaces. They are equal when the space, the distance is equal, but it's across the y or the x-axis. The second type of transformation is what we call the translation. So translation is a transformation in which every point in the figure is moved in the same direction and by the same distance. So translation are categorized as horizontal translation or vertical translation. So when can you say it's horizontal? If it is moving left or right along the x-axis. So it's horizontal x. Vertical, moving up or down along the y-axis. So when it's vertical, it's y-axis or a combination of the two translation. We're going to have that later on. So a vertical translation can be represented algebraically by g of x equals f of x plus k. This k determines whether it translates upwards or downward. When k is greater than 0, it translates upward. But when k is less than 0, it translates downward for vertical translation. So let's look at this. So this is your original line. So when it say translated up, because the vertical translation is 4 units upward. How do we know? Because of this plus. That means the k there is greater than 0 because it's plus 4. So it slide or move upward. How many spaces? 1, 2, 3, 4. Okay? Units upward. When it's less than, you see a negative 4, that means the k is less than 0. So it translates 4 units downward. 4 units down, 4 units down in all points in the graph or on all points of the line. For horizontal translation, it can be represented by an f. G of x is f times x minus h. You see that h there? When the h is greater than 0, it translates to the right. But when it's less than 0, it translates to the left. So you slide right or you slide left for horizontal translation. So in this case here, we have horizontal translation 3 units left. But you look at the symbol here, it's plus. You might think it's plus, you move to the right, or it's minus, you move to the left. It's the reverse. Because what happened is, inside the parentheses, it's x minus a negative 3. That's why it has an x plus 3. But actually, our h there is less than 0. So you move 3 units to the left. The movement is to the left. All right? Here, you have g of x, f times x minus 3. What happened inside the parentheses, it's x minus a positive 3. So, it's positive 3. That means the h is greater than 0. That's why it moves to the right. It slides to the right. So when you do that, be sure you do the inverse of the sign when it's horizontal translation. So like this, the graph is moved 3 units to the right. We have a vertical compression and stretch. Vertical, a transformation that makes all y values, because it's vertical, y values of a function and a constant factor towards the x-axis. It's compressed. But when the y values of a function of a constant factor away from the x-axis, it's stretched. So towards compressed, away it's stretched for vertical compression. Okay? So vertical compression, you have g of x is equals to a times f of x, where a is greater than 0 and less than 1. When it happens, it corresponds to compression. But when a, absolute value of a, is greater than 1, then it corresponds to stretch. All right, let's look at this. Vertical compression with a scale factor of a 0.5 f of x. So the a is less than 1. The absolute value of a is less than 1. It is compressed. So what happened is that the line now is compressed, move up, while here it is vertical stretch with a scale factor of 2. The g of x is, the a there is 2, and it is stretched because it's greater. The scale factor is greater than 1. For horizontal compression and stretch, a transformation of scales that all x values of a function factor towards the y-axis. Well, a horizontal stretch, a transformation where all the x values of a function is away from the y-axis. So you have a horizontal compression or stretch can be represented by g of x, f times the b of x. The b there is representing the horizontal or vertical stretch where the absolute value will be greater than 1 for compression. If it's less than 1, it is stretch. So the horizontal and compression with a compression factor of b equals 1 over the scale factor for the stretch. We'll have more example on this later on so that we can understand better. For horizontal compression, it is g of x equals f times 2x. So it's compression because the scale factor is 0.5. That's less than 1. That's why it's compressed in the graph. It's stretched here where the scale factor is 2. That's greater than 1. That means it is stretched like this in the case right here. Okay, in this graph. So when performing multiple transformation at one time, we use the standard form of the notation a times f times b times x minus h plus k, where the a, b, x, h, and k are all present. We have the a, we have the b, we have the h, and we have the k. All right. A and B stands for horizontal and vertical compression. H stands for the H stands for translation, and K as for translation up and down. All right. Let's have an example to understand more. A function is shown in the graph below. Determine the equation of the function after it has been reflected across the x-axis and translated 4 units to the left. So you have here reflected across the x and translated 4 units to the left. All right. If you have to think about it, you can have 2 ways in doing it. You can apply the transformation to the graph and then determine the equation of the final graph. Or you can determine the equation of the graph shown, then apply the transformation algebraically. So if we try to look at the graph here, we can have the slope of 1 over, try to look at this. It has a slope of negative 1 over 2 because it rises down and over 2. Okay, let's do that later. So choosing to apply, let's do the transformation first. Okay. Now it says that across the x. So when it's across the x reflected, all right, I'm going to erase this. Let's do some reflection across the x. I will use some colored. All right. So I choose a point. Okay. It's a reflection. So this is the x-axis. So I count 1, 2 spaces, so 1, 2 here for this reflection of this point. I'll choose this point. 1 space, so I move 1 space up. Let's say this point right here. 1, 2, 3, so I count 1, 2, 3. right here, 4 dots. So 1, 2, 3, 4, 1, 2, 3, 4. And this point will remain as is. All right, since it's actually the point on the X line. So I'm going to draw the reflection line. Okay, let's use a ruler here. So this is the reflection line. Okay. Now, after reflection, it moves 4 units to the left. So this point will move 4 units to the left. Say 1, I'll try to use another color to make this clear. So from here, 1, 2, 3, 1, 2, 3, this point. So from here, 1, 2, 3, 4. It moves 4 units to the left. Okay, so from here, 1, 2, 3, 4, the point now moves here. So in other words, I could have this point right here. 1, 2, 3, 4. Okay, let's draw the line. This will be now the new line that we're talking about after doing the translation. Okay? After doing, this is the translated. The new line. After translation. Alright? So at first, you do the reflection, and this is then you do the translation. Alright. Looking at the final graph, we can see that it is a straight line. Right? This is straight line. All are straight line actually. Okay. So which passes through the origin and has a slope of, let's say, 1 over 2. You go down 1 and negative 2. I'll go back to the color. So the slope is negative 1 over 2, as I've said before. So we can have the equation of the function from the linear function. Remember the parent function? So the parent function of a linear function is, we can have the g of x equals x times the negative 1/2. That would be negative x over 2. So if we try to do that thing, and our reflection across the x-axis is represented by changing the signs. So this is your equation of the line. You come up with the same results. Okay, let's do this. A point A, negative 3, 9 lies on the graph of f of x. Determine the coordinates of the corresponding point on the graph of g of x equals 1/3. All right, look at this. F times x plus 4. Look at this. So we have transformation that is taking place. So what are we going to do? We can use the given expression to determine the transformation from f of x to g of x. Then we can apply the transformation to point A. So in the expression of g of x, okay, g of x equals 1/3 f x plus 4. The plus 4 inside of the function, this plus indicates a horizontal translation of 4 units to the left. Okay, I'm gonna write this. 4 units to the left. Well, the 1/3 outside, what does it indicates? Isn't it a vertical stretch or compression or shrink? So vertical compression or shrink by a factor of 1/3. Okay, we have to identify that. So our point A is -3, 9, right? Shifting the points 4 units takes the point to 4 units. So 4 units to the left. So what happened? -4. -4 units to the left. This will become -7 and 9. The point is being moved. That is horizontally. So we are doing only the shifting on the x point and shrinking it vertically by 3, because 1/3 you get the factor by 3 results of what? 9, 1/3 of 9. 1/3 of 9 is 3. So we have a -7, and the 9 now is changed to 3 because it's shrink by 1/3. Okay? So we can also think a transformation of algebraically. So how do we do that? The only point we know on the graph of f is point A. Okay, that's the only point, which is -3, 9. So if we have a function of -3, which is equals to 7, then we can rewrite this to the correct form of g of x. So g of x as follows: f of -3 equals 9. So the function is -7 plus 4. That's equals to 9. That is rewriting a -3. We rewrite the -3. So -3 is 7, -7 plus 4 in the form of what would that be? Plus 4 in the, because it shifts 4 to the left. This plus 4 right here. So you have 1/3 of f times negative 7 plus 4 equals 9 times 1/3. We multiply 1/3 on both sides. So that would be function of negative 7 plus 4 equals 3. Then g of negative 7 is equals to 3. By using the definition of g of x. So the corresponding points is negative 7 and 3. We are just trying to prove that this is the corresponding points because you are asked find the coordinates of the corresponding point of the graph. So after doing the factor, the shrinking, and the how do you call this? Moving, translating 4 units, or how many units would that be? 4 units to the left with this. And you come up with the corresponding points. All right, let's do this. The graph of the function f is shown. So we could tell right away that this is an absolute value. So you are asked to determine the equation of the function has been translated 6 units to the right and horizontally stretched by a factor of 2. Okay, so we have an absolute value function. Remember the function family. So the graph has V shape. So V shape, as I've said, tells us an absolute value function. So the parent absolute value function is f of x is equals to the absolute value of x. That is the parent absolute value function. Parent absolute value function. Okay, so we need to give the transform function a new name, like the g of x, since we are creating a new function here. So we're going to write a new name by having it as g of x. A horizontal translation, that is 6 units to the right, and a horizontal stretch by a b and h, are represented by b and h. This is h and this is the b, the factor, right, in the function. So the new name, we can have it g of x. So the function parent, we have inclusive b times x minus h. For that, remember that the b is the stretch factor, horizontal stretches, so 1 over the stretch factor as mentioned above. All right, let's do this. So we're trying to figure out everything. So in this case, the stretch factor is 2. Right? The stretch factor is 2. That means the b is 1 over 2 because that's a stretch factor. To translate the function 6 unit to the right, so our h is 6. So to find the equation, it has been horizontally translated and stretched So using the g of x f, substitute the b, which is 1/2, then x minus 6. You have that as the transform function, the equation. So determine the equation after the function has been transformed. So how are we going to simplify this? We still can simplify. G of x can be multiplying 1/2 x minus 1/2 of 6, 6/2. That would become what? This would become g of x would be the absolute value of 1/2. Oops. This is an absolute value sign. 1/2 of x, 6 minus 2 is 3. You have this as the equation of the absolute value sign. Okay. So after simplifying the equation, this transformation that we applied on the graph are no longer easy to identify. If one is not careful, it might seem that this function was only translated 3 units to the right. However, that is not the case. We know that the function was translated 6 units to the right. So in order to identify the transformation, we given an equation, we must convert it to the standard form by factoring the coefficient of x. That's why we have the g of x. Okay, we can have the g of x equals a times f, the absolute value of b, this is the inclusive, x minus h plus k. Or the standard equation form, the g of x, in this case, will be the 1/2 x minus 6. That means this is the translated 6 units to the right, and this is stretched horizontally by a factor of 2. All right. Graph g of x. This is question B. Graph g of x and f of x on the same coordinate plane. If we are going to graph, let's apply this idea when we graph. Using a table of values of f of x, maybe this can help us in the stretch on the function horizontally. A table of values is given. So if we have a negative, this point right here, if we have a negative 4, the f of x is 4. We have a negative 3, a negative 2, it's 2. Negative 1, it's 1, that is in between. And then right here, for negative 3, 0, then 1 for 1, 2, then 3, and then 4. And just choosing these points from the table. So let's assume that these are the points that I found and making it a table. We can double the x values and leave the y values the same. Okay, how about if I double negative 4 and make that as negative 8, and negative 3 make that as negative 6. Negative 2 is 4, negative 1, negative 2, then I have 0, then 1, 2, 2, 4, 3, 6, and 8. So this is the output. It's still 4, 3, 2, 1, 0, 1, 2, 3, 4. What I did is just I doubled the x value, and let's see what's gonna happen. All right, let's do this. When x is negative 8, I have 4. I'll use another color. When x is negative 8, I have 4. When it's negative 6, I have 3. Somewhere here. When it's negative 4, I have 2. When it's negative 2, it's 1. And then 0. When it's 2, it's 1. Then when it's 4, it's 2. When it's 6, it is 3. When it's 8, it is 4. Okay, let's draw the line. Might as well I choose another color for that. Say this color. So what did I have here? It's stretch. From this green one, it's stretch. Okay. So after stretching, we simply need to shift all the points on the graph 6 units to the right. All the points in the graph 6 units to the right. So what will I do? From here, I move 6 units. Let me use another color. So if I move the 0 6 units, it will be here. All right. What other points will I move 6 units? This point. So 2, 4, 6. It will be this. Maybe I can have that. And which point from the other side? 6 units to the right. So I have 1, 2, 4, 6. This point right here. And here 2, 4, 6. This point right here. Let's look at our new graph that has been moved. Okay, let me use another color for that. Okay, this one. This one is now the new figure. After stretching and after translating. This is the new graph. All right. After you translate and then after you stretch. Okay, I'm going back. All right. Let's have this example. Describe how g of x is equals to 3 to the power of x minus 5 minus 6 has been transformed by a parent function. What is this kind of function do we have? So what would be our exponential? Because it transformed very, very increasing fast. All right? 3 to the power of x. That's the, when you see this graph right there, it's exponential. Increasing fast. So when we compare the f of x with the g of x, we can see that there are numbers that had been added and subtracted. So there is a minus 6 here. So addition and subtraction can be used to represent the translation. So negative 5 is subtracted from the input value of x minus 5. Right? So we can write that g of x is f of x minus 5 minus 6 by doing that. The graph of g of x is the graph of f of x, and it has been translated 5 units to the right. So 2, 4 going here and goes down with 5 units. Okay? And down 6 units, 2, 4, 6 units here. Okay. When we graph, we reflect, we can see that the f of x has been shifted 5, 2, 4, half of it is 5, and then go down 6 units. All right. That's it. That is how we describe the graph. So the function of x has been shifted. What's the shift? 5 units and down. This is shifted 5 units right and down 6 units to obtain this graph. Okay, that's it. We'll have more on this in the problems and solutions. So reflections and translations, we summarize as follow, using this as our the how it is written algebraically, where A is the vertical, B is the horizontal stretch or compression, vertical horizontal translation. So A is greater than 0, no reflection. A less than 0, reflection across the x axis. Absolute value of A greater than 1, vertical stretch. A is less than A is greater than 0 but less than 1, vertical compression. The K is greater than 0, we have vertical translation up. K is less than 0, vertical translation down. For B, greater than 0, no reflection. B less than 0, reflection across the y-axis. Absolute value of B greater than y. Horizontal compression. B is greater than 0, less than 1, horizontal stretch. The H is greater than 0, horizontal translation to the right. When H is less than 0, horizontal translation to the left. We're going to go over this and have more works on the problems and solutions about translations, reflection, vertical, horizontal translation, vertical, horizontal stretch, and compression. Okay, let me say this. If I can do it, so can you. Don't forget to hit the like button and subscribe button. See you in my next video.